Hello everyone, this is Anudh Mishra. I'm an MBBS student at AIIMS Bhuvneshwar. Last session we were discussing the chapter Principles and Processes of Isolation of Metals. Okay, we had completed the first two processes, which were enrichment of the ore or purification of the ore and converting the ore to oxide. We had covered the basics of reduction of the oxide to get the free metal. Yesterday we stopped at Ellingham diagram. So we have discussed the Gibbs free energy criteria, entropy criteria, enthalpy criteria, equilibrium criteria, which are necessary to temperature criteria, which are necessary to shift the reactions to a spontaneous direction. And all of you know that the reduction of metals from the oxides or any other compound requires lot of temperature because the enthalpy of the reaction is too much positive. So to drive the reaction, to make the delta G negative, there are two ways. Either you add a reducing agent whose enthalpy or whose Gibbs free energy change is really negative or highly negative. Otherwise, otherwise you just increase the temperature so that the Gibbs free energy change becomes negative. That's the role of metallurgist. So they determine which one is more feasible and economical to increase the temperature or to add a suitable reducing agent. So both of these terms can in fact be presented in a diagram called Ellingham diagram. It is a graphical representation of Gibbs energy versus temperature. Okay. So it is very useful in predicting the feasibility of thermal reduction of an ore. Let us see the points. It consists of Gibbs energy change versus temperature for formation of oxides of element. So the general reaction is something like this. In this reaction, the gaseous amount is decreasing from left to right due to the consumption of gases, leading to a negative value of delta S. So delta S is negative here. Entropy change is negative. Why? Because gas is being consumed. It is being turned into solid, so delta S is negative. Also, enthalpy is really positive. Okay. Subsequently, delta G shifts towards a higher side despite rising temperature. Okay. The result is a positive slope in the curve for most of the reaction. Each plot is a straight line, except when some change in phase, there is a kink. Okay. If there is a change in phase, it is increased, it is indicated by increase in slope on the positive side. Okay. For example, for zinc, ZNO plot, the melting is indicated by abrupt change in the curve. Otherwise, they are straight lines. Now, there is a point in a curve below which the delta G is negative. So, the metallic oxide is more stable because it is the formation of metallic oxide. And if the delta G for formation of metallic oxide is negative, so that oxide is going to be more stable. Above this point, the oxide must decompose on its own because it is not stable, it is not spontaneous. We will see everything, don't worry. In an Ellingham diagram, the plots for and free energy change of common metals and some reducing agents are given, okay, at different temperatures. So the limitations we'll discuss after we are done with the diagram. I'll take you directly to the diagram. This is the Ellingham diagram. Let us take a small example and try to understand this diagram. The example which I'm going to take is carbon monoxide turning into carbon dioxide. So basically it is this curve. If you can notice, I'll zoom it. Look at this curve. I'm drawing a line also. So you can see that this is a straight line. This reaction will never go any kind of phase change because this is a gas, this is a gas, this is also a gas. So there are no kinks. This is a straight line. First point. Second point, you can see the delta G is plotted on the y-axis. So basically you can see the formation of CO2 in most of the temperature range. The formation of CO2 from carbon monoxide and oxygen, it is negative only. Delta G is negative only. Okay. So it is a feasible reaction. Now, suppose you want to reduce Fe or you want to reduce zinc oxide. Okay, you want to reduce zinc oxide using carbon monoxide as the reducing agent. So this is the reducing agent. We are talking about this reaction now. Okay, got it? This reaction shows zinc is being converted to zinc oxide. So suppose I have to decompose ZNO to the zinc and oxygen. Then what is the problem here? We have to reverse the values of delta G because it is the reverse reaction. So let us take a suitable temperature in which the total value of delta G would be negative. Okay. Can you find such a temperature? Let us see. At this temperature, suppose this temperature is X. Delta G for carbon monoxide to carbon dioxide, it is minus 500. And the delta G for the zinc reaction is somewhat around plus 610, we can say. So this will result in a positive delta G. So this is not the temperature we are looking for. Let us take a still higher temperature. Again, you can see that the delta G for your carbon monoxide conversion is somewhat minus 300, but the delta G for the zinc one is plus 400 something or plus 380 something. Again, we cannot obtain a negative value. So until and unless these curves intersect each other and the metallic curve comes above the reducing agent curve, metallic curve comes above the reducing agent curve, you cannot find a suitable temperature in which the delta G will be negative. So I give you a shortcut here. Find out the point of intersection. Okay. And after the point of intersection, above it, there will be lots of temperature where you can find a net delta G negative. If I take an example of, suppose, reducing iron oxide. So where does it intersect with the carbon monoxide curve? It intersects somewhere here. Above it, beyond it, you can find, suppose at this temperature, I have to erase all of it. This is the final thing after which we'll move forward. So I'm erasing everything. See, this is the temperature of this is the point of intersection. Above it, I take any temperature. Suppose I take this temperature. Here, for the carbon monoxide curve, suppose the delta G naught is minus 300. For the iron oxide to iron curve, the delta G naught will be plus, suppose, 220. So the net delta G naught will be plus 220 minus 300. That will be minus 80. So it is spontaneous. You go still higher temperatures, it will increase because the curves are separating from each other. Got it? How to use an Ellingham diagram, Ellingham curve to predict spontaneity. They have given example also. They have taken point A as the point of intersection and their reactions are these two. So we'll just discuss this also. But before that, let us move where we had left yesterday. Limitations. We'll just move to limitations first. Limitations of Ellingham diagram is, just a second. Limitations of Ellingham diagram, the curve just indicates whether a reaction is possible or not. The tendency of reduction with a reducing agent is indicated. Okay. It cannot answer questions like how fast it could be. No fast, slow, it will not just answer, it will just predict if it will occur or not. Then interpretation of the change in Gibbs energy is based on equilibrium constant. Okay. Thus, it is presumed that the reactants and products are in equilibrium, which is also not a correct presumption. Okay. So it presumes that they are in equilibrium and it is a wrong presumption. This is not always true because the reactants and products may be solid. Okay, so these are the two limitations. Let us move on. Moving on, applications of aluminum curve. First application is extraction of iron from its oxide. So how do you explain how iron is smelted? Okay, this we'll see here. What processes we use? See, uh, how do you, after the calcination and roasting, limestone is mixed, coke is mixed, and it is fed into a blast furnace. So after concentration through calcination and roasting, all these steps occur. Then the oxide is reduced to metal. How? So one of the main reduction steps they have given, FeO plus coke, this is coke, gives iron and carbon monoxide. It can be seen as a couple of two simpler reactions, which are these. So these two reactions, there will be individual delta G's, and we can correlate it with the, we can correlate it with the aluminum curve. See, Fe to FeO and carbon to this. So they are talking about this curve and this curve, right? See, after a temperature of about 673 Kelvin, at any point of time, the metallic curve is above the reducing agent curve. So you will get good results after 673 Kelvin, which is the point of intersection, right? Going on, when both the reaction takes place, the yield of the equation, they have added it. So equation should be negative. The delta G naught should be negative. The curve of carbon monoxide goes downwards as the at temperatures above 107 K approx, the carbon monoxide line comes below FeFeO line. Okay, so they have taken it here. Carbon monoxide line, FeFeO line at 1073 Kelvin. So I think it is, they have taken a different curve. Anyways, if they are telling you it's 1073K, it is 1073K. Okay, right. So below the line, the delta G difference will always be negative and reduction will be possible. Okay. In the blast furnace, reduction of iron oxides takes place at different ranges. Hot air is blown from the bottom. Temperature is about 220, 2200 Kelvin in the lower portion itself. Burning of coke supplies most of the heat. Okay. Carbon monoxide and heat move to the upper part. In the upper part, the temperature is lower, and the iron oxides Fe2O3 and Fe3O4 are reduced in steps to FeO. So in the upper part, Fe2O3 and Fe are reduced to FeO. Now, the reactions have been summarized in the upper part. The Fe2O3 is reduced, Fe3O4 is reduced by coke to basically FeO in the end. Okay, so they are coupled reactions. Then a bit higher temperature, middle temperature range, carbon and FeO, the main reaction occurs, which we had discussed earlier. Now, the important point, limestone is decomposed to calcium oxide. Okay, it removes silicate impurity as slag. How does it remove the silicate impurity? Look at this reaction. This is the slag formation reaction. So calcium carbonate or limestone gives calcium oxide. Calcium oxide with SiO2 gives calcium SiO3, that is a slag. Okay. Here, molten slag is collected separately. Now, iron obtained from blast furnace has 4% of carbon and some impurities Sp, Si, Mn. So it is known as pig iron. Then cast iron. What is cast iron? Cast iron is different from pig iron. It is made by melting pig iron with scrap iron and coke. Okay. It has lower carbon, 3% carbon. So yeah, we have discussed two kinds of carbons, two kinds of iron, pig and cast. So two irons we have discussed. What is wrought iron? Wrought iron is the malleable iron and it is the purest form of commercial iron. Now this is the third form of iron after pig and cast. You have the wrought iron. It is made from cast iron by oxidizing impurities in a reverberatory furnace lined with hematite. Okay. The hematite oxidizes carbon to carbon monoxide. So this is the first reaction. Here you obtain iron known as wrought iron. Okay, got it. Here also limestone is added and the sulfur, silicon, phosphorus are oxidized and passed into the slag. Then iron is done. The second application is copper. How do you extract copper from cuprous oxide? Look at the curve for copper, the Cu2O line. So it is quite easy to reduce oxide of copper by heating the metal directly with coke, because all the lines of carbon, carbon monoxide, carbon to carbon dioxide are much lower position. Okay, so the temperature is kept low. However, most of the ores are sulfide and may also contain iron. The sulfide ores are roasted and smelted to give oxide. So this is the roasting of sulfide ore. Then oxide can be reduced to metallic copper using coke. So these are the two processes. In the actual process, ore is heated in the reverberatory furnace after mixing with silica. Silica, why? Because it will remove the iron impurity. Okay. And the copper that is produced, it is called copper matte. It contains these two compounds. Copper matte is then, so after getting copper matte, you charge it into a silica line converter and these reactions occur. So FeS is turned to FeO, FeO is turned to FeSiO3. This is the slag formation. The reaction of our concern is Cu2S is turned to Cu2O and Cu2O is turned to copper. So what is happening for copper? To extract blister copper, this is blister copper because evolution of SO2, this is the metal, there SO2 is evolving, so it will form blisters. So to make blister copper, what you have to do? You have to first take basically sulfide, roast it to oxide, then again convert it to, reduce it to sulfide only. What is this? This is called copper matte, then again convert it into copper metal. So yeah, these are the steps for copper. Copper clear? Okay. Last one is extraction of zinc from zinc oxide. It is also done using coke. The reaction is given here. Okay. Now, here also you can see coke is added to the zinc oxide and it gives Zn plus carbon monoxide. So this was all about reduction of metal, applications of Ellingham diagram. The next thing which we will be covering is your electrochemical principles and refining. So first we need to know the electrochemical principles. The basic concept which we are studying here is Gibbs free energy change, right? So the Gibbs free energy change is delta G naught, and it is related to the electrolysis by this equation. This is Faraday's equation. Okay. So here E naught is the electrode potential, N is the number of electrons. Okay. And F is the Faraday's constant. Okay. More reactive metals have large negative values of electrode potential, so the reduction is difficult. So if the difference of two electrode potential values corresponds to a positive electrode potential and consequently a negative delta G naught, then less reactive metal will come out of the solution and more reactive metal will go into the solution. So this is what is happening. Here the E naught of the cell is positive, so the less reactive will come out, which is the copper. It will come out as copper solid and iron will go into the solution as Fe plus 2. Now in simple electrolysis, what happens? Ions are discharged at the electrodes. So cations are discharged at the cathodes, okay, and deposited there. So they are deposited at cathode. So cations are attracted towards cathode and they get deposited there. Precautions are taken considering the reactivity of metals. We will see how to electro-refine aluminium. Now, purified Al2O3 is made by mixing with Na3AlF6 and CaF2. These are the lowering of melting point. They cause the lowering of melting point and increase the conductivity. So, Na3AlF6 and CaF2, they are called cryolite. This is called cryolite. It is added to lower the melting point and increase the conductivity. They might ask you in exams. So remember this. It is done in a steel vessel. Lining of carbon is there. It acts as cathode, and graphite is there, which acts as anode. So carbon C, cathode C. Graphite is the anode. What happens is this reaction. Al2O3, 3 carbon, it is reduced to aluminium and CO2. This process of electrolysis is known as Hall-Heroult process. All of these points you need to remember whatever I've underlined. So next, we have got aluminum in this process. The oxygen liberated at anode reacts with the carbon of anode to produce CO and CO2. This way, for each kilogram for aluminum produced, 0.5 kilogram of carbon anode is burnt away. The electrolytic reactions they have given here. First, cathode formation. The cations are there. The cations are converted to metal. Anode, anions come. They are oxidized, okay, either to carbon dioxide or carbon monoxide. So there are three products. These three are products. This is we have done the aluminium part. Now let's do copper extraction from low grade ores and scraps. Hydrometallurgy, it is leached out using acid or bacteria. The solution containing cupric ions are treated with scrap iron or H2. So cupric ions with H2 gives H plus and copper, because in the reactivity copper comes below hydrogen. For example, sodium is here, then hydrogen will be somewhere in the middle, copper will be even below hydrogen. So H2 can displace Cu plus 2 and it will form H plus and Cu solid. This is what is happening. So we are getting copper metal. Then oxidation and reduction. Some extractions are based on oxidation, particularly of non-metals. A very common example is extraction of chlorine from brine. So how do you extract non-metals? How do you extract chlorine gas? You oxidize it in presence of water. The delta G for this reaction, E naught is minus 2.2. Naturally, it will require an external EMF because electrode potential is minus 2.2. So we need an EMF greater than 2.2. But electrolysis requires an excess potential to overcome some other hindering reactions. Thus, Cl2 is operated by electrolysis. Okay, electrolysis of molten NaCl is also carried out, but in that sodium metal is produced and not NaOH. So here, if they ask you Cl2 the production, so two methods are there, either brine or NaCl molten. So both of this, if you do electrolysis of brine, you'll get Cl2 and NaOH. If you will do the electrolysis of NaCl, you will get sodium metal and chlorine gas. Then gold. Gold, silver, or etc. They involve leaching the metal with cyanide ion. Again, you have the first reaction. Here, gold, cyanide ion is there. It will form a complex with cyanide ion. Now, this complex with a reactive metal will the reactive metal will go into the complex and gold will be deposited. So yeah, that is what you need to remember, that gold complex, put a reactive metal complex plus gold. So this is how you extract gold. Now we come to the last part of the chapter, that is refining. So we'll start from okay. So what is refining? Okay, a metal is extracted by any method, usually contains some contaminant or impurity. For obtaining metals of high purity, several techniques are used. And the techniques are distillation, liquefaction, electrolysis, zone refining, vapor phase refining, chromatographic methods. Remember all of these techniques by names because they will ask you this in MCQs, like something like which of the followings are not a method of refining metals. So you should remember these. Going to the first process, which is known as distillation, the point that I'm underlining are to be remembered. It is for low boiling metals like zinc and mercury. Impure metal is evaporated and pure metal is obtained as distillate. Only this much you need to remember. For liquefaction, low boiling point, here it is low melting point metal, like tin. It is made to flow on a sloping surface. This way it is separated from a higher melting impurity. What happens is the obtained metal is here. A sloping surface is heated. Okay. So all the tin will melt and get collected here. So this is highly pure tin and the impurity will stay here only. It will not melt, it will stay there only. Then electrolytic refining. Everyone has seen electrolytic refining. We have learned about this in lower classes. I'll just draw, I think they've drawn the cell also. Draw the cell. No, they've not drawn the cell. I'll draw the cell, electrolytic cell for the thing. So here the impure metal is anode. Suppose you're taking copper. So impure metal, this is impure metal. This will be the anode or the positive electrode. This is a very thin strip of pure metal. So pure you will keep thin only because impure metal will come and your what get deposited here. So this is your pure metal, which is the cathode. Solution is of copper sulfate because you need copper ions. So what happens is copper ions are liberated here. Okay, copper ions are liberated. They go into the solution, form copper sulfate. Copper sulfate, some copper ions are getting deposited here. So gradually, this will be filled with copper. The thickness will increase, and this will be completely filled with the pure copper. So copper is refined, anodes are of impure copper, pure copper strips are cathode, acidic solution of copper sulfate is the electrolyte, and these are the reactions that occur basically at cathode. Copper is being deposited. Impurities from the blister copper deposit as anode mud. This is important. Anode mud, it contains antimony, selenium, tellurium, silver, gold, and platinum. So some anode mud will be deposited here near the anode. Zinc may also be refined this way. Next, zone refining. This is also a really frequently asked question. What happens here is impurities are more soluble in the melt than in the solid state. So if there is a melted metal, here impurities will be dissolved very easily. But if you have a solid metal, impurities will not be able to dissolve. So impurities will be separated. If you give impurities a choice, they will choose the melted form to get dissolved. So what has happened here is a mobile heater is fixed at one end of the rod of the impure metal. It is moved, okay, and this is the heater. This is the heater, okay. Wherever it moves, some part of metal it starts melting, which is near the heater, and the because it has started from here, so this melted part keeps on moving with the heater also. Okay, the melted part also keeps on moving. As the molten zone moves along the heater, pure metal crystallizes out of the melt and impurities pass into the adjacent molten zone. That is what happens. Okay, this process is repeated several times. Heater is moved in the same direction. At one end, impurities get concentrated. This end is cut off. This is useful for producing very high purity metals for the purpose of semiconductor. So examples they will ask: germanium, silicon, boron, gallium, indium are refined this way. Copper and zinc are refined this as electrolytic refining. Tin is refined as liquefaction. Zinc and mercury are refined as distillation. Next is your vapor phase refining. In this method, the metal is converted into its volatile compound and collected elsewhere. It is then decomposed to give pure metal. So metal is converted to volatile compound. It is collected and then again decomposed. There are requirements. Metal should form a volatile compound with an available reagent, and the volatile compound should be easily decomposable so that metal can be recovered. First, MODS process. It is for nickel. So nickel forms a volatile compound with complex with carbon monoxide, and this is easier to decompose also at a bit more higher temperature. Then is your von Arkel method for refining zirconium or titanium. They form complexes with iodine, and they are heated at 1800 Kelvin to get the metal back. Then is your chromatographic methods. The chromatographic methods are based on the principle that different components of a mixture are different adsorbed. So mixture is just like how chromatography is done. There is a medium, mixture is moved through the medium, different components are adsorbed at different levels in the column. Now they are removed by using suitable solvents. So here you can see that there are color bands. So you have put a mixture and they have been separated. Now you can easily remove them individually. This is the principle of chromatography. Examples you need to remember to separate Al2O3. Okay, this is a good example. Then uses, we are at the end of the chapter. Uses: aluminium foils are used as wrappers for chocolates. Paint, aluminum is used in paint and lacquers. Then extraction of chromium and manganese from oxide. Aluminum wire, electricity conductors, alloys, all of this is aluminum. So remember all the uses also. For copper, wires, water, steam pipes, alloys. You need to remember all the alloys. Brass is copper and zinc, bronze is copper and tin. So don't get confused with The Z in bronze, it is with tin. It is not with zinc. Zinc is with brass. Okay. Then with nickel, it forms the coin alloy. This is for copper. Now zinc. Zinc for galvanizing iron, batteries, alloys, brass, German silver. Okay. Reducing agent in manufacturing of dye, paint. This was zinc. Lastly, you have iron, cast iron. It is used for stoves, railway sleepers, gutter pipe toys. Okay. For making wrought iron and steel. Now, wrought iron, it is used for making anchor, wire, bolt, chain, agricultural implement. Steel. Steel is there. Alloy steel is obtained when other metals are added to it. Nickel steel is used for making cables, automobiles, aeroplane part, etc., etc., etc. See, chrome steel is for cutting tools, crushing machines, all sorts of equipment like that. So this is the chapter we have done. We'll go to the previous year questions. So guys, the first question is you have to match river battery furnace, electrolytic cell, blast furnace, zone refining. So zone refining definitely for silicon. River battery furnace for copper, electrolytic cell for aluminium, blast furnace for pig iron. So we have the option number one as the correct option. Next question. Mond's process for refining of Mond's process is used for refining what? Nickel. Where is the Mond's process? Nickel with carbon monoxide will form a complex, which is this. This is the correct one. Then, during electrolytic refining, pure metal is made to act as anode, and impure metal is act as cathode. This is wrong. Impure is anode. Then, second statement says during Hall-Herold process, purified Al2O3 is mixed with Na3LF2. So, firstly, purified Al2O3. It's not purified. Anyways, we can say purified Al2O3. Anyways, is mixed with cryolite to lower the melting point of the mixture. It is correct. We had seen cryolite was mixed with Al2O3 to lower the melting point and increase the conductivity. So statement 1 is incorrect and statement 2 is correct. Which of the following statements is incorrect? Boron and indium can be purified by zone refining method. Van Arkel method is used to purify tungsten. Cast iron is obtained by making pig iron, melting pig iron with scrap iron and coke. The malleable iron is prepared from cast iron by oxidizing impurities in a reverberative furnace. So this is correct. This is correct. This is correct. This is the wrong option. Van Arkel is for zirconium. Next, Asherson Ellingham diagram, oxidation of carbon to carbon monoxide, which is this. Shows a negative slope. Definitely, it has a negative slope. Carbon monoxide tend to get decomposed at higher temperature. So, at higher temperatures, yeah, you can say that is the reason. So, both are correct and R is the correct explanation. Then, okay, 11th. See, carbon monoxide tends to get decomposed at high temperature. So, at higher temperature, this reaction is more favorable rather than this reaction. So, this is a wrong statement. So yeah, A is correct, but R is not correct. Next, we go to the next unit. Which of the following reduction cannot be carried out with coke? So this can be carried out with coke? No. This can be carried out. All can be carried out except aluminum. It requires electrolysis. Now, point of intersection and sudden increase in slope respectively indicate. So point of intersection is delta G naught is equal to 0 and yeah, melting or boiling point. So this is the correct. Kink means melting and boiling is occurring. Then chemical that is added to reduce the melting point of the reaction mixture for aluminum, cryolite. Mercury, copper, silicon, nickel. Silicon is for zone refining, phase vapor phase refining is for, sorry, distillation is for mercury, vapor phase refining is for nickel, electrolytic refining is for copper. So yeah, third is the correct option. So we are done with the chapter, guys. Thank you very much. Wish you a best of luck for your JEE main. Goodbye.